that f1 of theta, this thing is equal to minus 2m over h cut squared 1 over q integral 0 to infinity r prime sine of qr prime v of r prime dr. Right? Questions? Okay. So, what is q? If there are no questions.
R prime minus R.
R prime minus R, no.
R minus R.
No.
R minus X.
Say? Yes, it is the momentum transfer. The momentum change that occurs, right? So this was K, this was Ks, and this was Q. Right? This angle is theta that appears here. So this is the probability of being scattered. Well, the square of that is the probability of being scattered in the theta direction. Okay. Fine. So, and so maybe I do need to remind you that Q is 2k sine theta over 2. So this is where theta is hiding. Okay, so now let's take an example. Let's take this V of R to be V naught e to the minus mu R over mu R. And this is a very special type of potential.
Yes.
Right? So if you forget this, for mu is equal to 0, this is the Coulomb potential. And otherwise this is called the Yukawa potential. This is the range. This is the range. Basically, this is related to the mass of the exchange particle, or whatever. You don't have to talk about the exchange particle there. This is just the range of the potential. So both V naught and mu are constants. So for this potential, how would you calculate the first order scattering cross section? Well, you will not do anything, just put this in here in the integral. Second? No, you don't need anything. You don't need anything. This itself is the thing that you want to calculate. We did take the initial state, put it in for the scattered state, and calculated the first order cross section. Right? If you were to take this first order, if you were to take the new psi plus put it in for the old psi in that equation, what did you call it? Schwinger-Lippmann equation. The expansion of the Schwinger-Lippmann equation. If you were to put this now back into that, you will get the second order. Then if you were to take the second order wave function, put it back in there, you get the third order approximation, and so on and so forth. Right? So this is just the first order, which means that in that formula, there was a V psi plus here, right? So instead of this psi plus, you put in 5. And that gave you this F1. I thought there were no questions. Okay? The good thing about us is never afraid to ask questions. Although she's not sure going home and studying. Anyhow, so just put it back in there. Minus 2m over h cut squared 1 over q. Okay. And then you can just take this v naught over mu outside. 0 to infinity e to the minus mu r sine of qr dr. Then just replace this with e to the iqr minus e to the minus iqr over 2I, right? And you will get an integral. So this integral is going to look like this: 0 to infinity e to the minus mu minus iq. And then there will be another integral 0 to infinity e to the plus or minus mu plus iq dr, and you know what the answer is. So this is going to look like this: 1 over mu minus iq minus 1 over mu plus iq. ठीक है? तो कर लोगे ना? ठीक? So, what you get is this, for F1. What you get is 2m over h cut squared, v naught over mu q, 2iq over mu squared plus q squared. There is another 1 over 2i. Right. So that is just cancel. So that's what you get. 2m v naught mu h cut squared. Oh, so q also cancels. So okay, so that's your answer. Now, if you want to calculate the probability to be scattered in a certain direction theta, how would you proceed? So this is F1 of t, F1 of theta in some sense. Now what? Basically you have to calculate d of theta. By the way, आप चाहें तो इसको अगर आप थीटा की फॉर्म में पर्टिकुलरली लाना चाहते हैं, you can write that as v naught over mu 1 over mu squared plus 4 k squared sine squared theta over 2. Is it looking like something that you've already seen? We don't really listen. रदरफोर्ड फॉर्मूला याद है? याद तो नहीं होगा। There is one more simplification. If you want it to look more like that, then this thing 4k squared sine squared theta over 2. This can be written as 2k squared 2 sine theta over 2, right? Sine theta over 2. What is this equal to? Again, so this is 1 minus cos theta over 2. So this is 2k squared. So q squared is basically equal to this. So if you want, you can just replace this thing with mu squared plus mu squared plus 2k squared 1 minus cos theta, and this 2 goes away, right? Is there mistake there?
It's actually 1 minus cos theta.
So
2 नहीं आएगा, तो already figure 2 minus.
और ये 2 नहीं आएगा, 2 नहीं आएगा, बाकी बात है?
So,
नहीं, ये तो q square लिख रहा हूँ ना,
ठीक है.
बस ये मुझे समझ नहीं आ रहा कि 2 यहाँ पे है या नहीं है,
है.
बस ठीक है, नोट्स में भी है. अच्छा, so now d of theta, what is this equal to? And you see the approximate. Yeah, come on. Square actually. So this is going to be 2m over h cut squared v naught over mu squared 1 over 2k squared 1 minus cos of theta plus mu squared. Okay. So if you take, now how do we reduce this Rutherford's formula?
Why is it the approximation?
Why is this what?
Why did you put the approximation?
Because d theta, this is only the first contribution to d theta. So there are an infinite number of them, but this is the most prominent one. And usually if you calculate the first couple, you're good enough. And so in this case, just the first one gives you the Rutherford's scattering formula. But it's still not Rutherford's scattering formula, because Rutherford's scattering formula was scattering from which potential? Coulomb potential, right? So how do you reduce this to Coulomb's potential?
You have to put that.
We bata दें. So mu goes to 0 such that v naught over mu is a constant, and that constant is equal to z prime over e squared over just that's it. And so if you plug these values back in there, f1 of theta, this is going to be, yeah, any questions? You look puzzled.
Why is v dot a very constant if mu is going to be?
V is also going to 0. V naught is also going to 0. This is the way of taking the limit. You're taking this to 0, but you're keeping this constant. Both of them are approaching 0 at the same rate. Right? Which means that, so if you do this, this will become, where is it? There, V naught over mu will become ZZ E squared, and then you will have V is equal to ZZ prime E squared over R. This 1 over 4 pi epsilon naught is 1. Or if you want, there is, this is K. There is a K there. Okay? So in that case, that K, I mean 1 over 4 pi epsilon, this is not the same K as this. 1 over 4 pi. Okay, so d sigma over d omega, this is going to be approximately equal to 2m squared z prime e squared over h to the power 4, 1 over 16 k4 sine 4 simplify it further, you can convert this K4 H cut 16 into energy over 2m. Energy is H cut squared K squared over 2m. And so this thing is 1 over 16 z prime E squared over E K squared 1 over sine 4 theta. Yes, questions? Any comments? Complaints? So basically, given a form of V, we can calculate d sigma by d omega to first order using this formula that we started with today. Okay, so here are a few things about first bone approximation. Yeah.
What is easy, right?
Oh, you're just trying to reduce it to the Rutherford's formula, right? So what was Rutherford's calculus? Oh, so there were these gold foil. You remember that? Gold foil and alpha particles.
Studied some
Yeah. So
15 years ago. I don't know.
yeah. So the potential between them is between the two nuclei is just z e squared over r. So that was the experiment that led to the discovery of nucleus. Okay, so f1 of q, f1 is a function of q only, right? And it depends on theta through q and only through this variable. Okay. You can choose it to be real. You can, if you look at the formula, we have put it in a form where it is real. Right? This is Hermitian, this is real. Q is real. Q is just that thing that I wrote somewhere, right? 2k squared sine, blah blah. Nothing here is imaginary or complex, right? Which means that it's basically the square of f1 of theta that you're taking, and you don't have to take the mod. So and another important thing, it doesn't depend on the sign of V, right? Right? Why? Physically it should. I mean, if it is an attractive potential or repulsive potential, it should make a difference, right? A repulsive potential will sort of repulse the particles, and attractive potential will attract particles. So it would depend whether your nucleus is negatively charged or positively charged. Why would it make a difference?
So scattering F mod to negative positive or F mod negative.
Fine, but why does it not depend on the sign of V? That's the question.
Because it scatters it in either direction in the same to the same
Yes.
degree.
That's right. Understand that? Okay, fine. Okay. For small k, right, you can further simplify the formula. For small k f1, so this thing is minus 2m over h cut squared 1 over q 0 to infinity r sine of qr v of r dr, right? And so for small q meaning? Small q, what does small q mean?
Minus cap.
The momentum transfer is small. Okay, so so the deflection is not appreciable. Okay, so in that case, this thing is just qr, right? And this q cancels, and what you're left with is something like this: r prime squared v of r prime dr. And if you were to sort of multiply with 4 pi and divide with 4 pi h cut squared, this would become d3r v of r. Right? So f1 of theta is something like this for small q. Right? So what is this? All that you're doing is just sort of integrating over the appreciable region where the scattering occurs. Okay? So this is small, and so there is a small region in which there is appreciable amount of scattering happening, deflection happening. So we're just integrating over there. And this is independent of theta. There is no q in there. So would this thing become better? So if I were to replace this, would this thing become better at large energies or worse? The approximation. It would get better, right? You can actually show that. I'm not going to go into that. But basically what you're saying is that Q sort of appears here, right? So this is going to become smaller. This is just rapidly oscillating. So it'll again become smaller, right? And so you'll converge very fast. So, so if the bond approximation is sort of valid at small energies, then it's definitely valid at large energies. It's basically what you always have seen. If the incoming particle has large kinetic energy, it doesn't have enough time to interact with the scattering center. It just sort of grazes and passes by, and so so Q is not appreciable in that case. Any questions? Let me give you a reading assignment because I want to finish with the bond approximation here, so that I can start with perturbation theory in the last week. So let me give you a reading assignment on the validity of bond approximation. It's a nice read. You can do it from Shankar or Sankara or both, and so this discussion here on page 398 through 400, or there is some in Shankar as well. Just read through it. It tells you when you can use the bond approximation. Basically what it says is that if V becomes too large, then you cannot use it. And since we're using perturbation theory, well, we already know that, but it actually gives you certain estimates for, let's say, for certain potential types, where it comes out very naturally. Okay. For example, if you have a potential, an attractive potential, and you can make a bound state, then if your incoming energy is smaller than the binding energy of the system, right, then bond approximation is not going to give you the right answer. Your energy has to be high enough so that you don't make a bound state. Okay, so you have to be able to sort of just see the potential and go with it. So just read through. If you have any questions, we can discuss them in the next class. Okay, so higher order bond approximation. Now, as I just told you, you can just keep on doing whatever we started doing. You can just take the wave function that you've calculated in the last order, use it in the next order, and get the next order bond approximation. Okay. But we have a better way of dealing with this thing, explained very lucidly in Sakurai. I'm going to follow Sakurai on this. So basically, what do we have to do? We need to express V, this term, right? You guys remember? Do I need to remind you what I'm talking about? So psi plus was phi plus some term which had V in it and psi plus, right? So it was this term that was problematic, okay? Because we were writing psi in terms of psi, so we don't know how to do it. So the way we did it was that we, in the zeroth order approximation, you put V is equal to 0, psi is equal to phi, then you take this, you put it back in here, whatever psi you get in the next stage, you put it back and get next order psi. Okay? So it is this term that we have to be able to write down. So in terms of phi, right? So we're going to write it like this. This was the incident wave. And this is called the transition operator. So it transitions you from this state to this state. Okay? So if you use this, then you can write psi plus equal to phi plus 1 over E minus H naught plus iota epsilon V of psi plus, right? So, okay, yes. So this is the equation that we want to solve, right? And it is this part that is making trouble. So let's put V here. Okay? Now this V of psi is just this thing, so this becomes T of phi is equal to V of phi plus V 1 over E minus H naught plus I epsilon. Here is what I'm going to claim. So I'm going to claim that this implies that T is equal to V plus V 1 over E minus H naught plus I epsilon T.
And so T is what
it is just defined by this equation. So if you're asking for the name, this is called the transition operator. Yeah, what? Yeah, again, equation again. Okay?
So ये higher order नहीं दिखाया.
ये तो इक्वेशन हमने लिखी है कि ये एक स्टेट है इनवर्ट स्पेस में, उसके ऊपर ये ऑपरेटर अप्लाई करता है, कोई और स्टेट बन जाएगी। ये एक और स्टेट है, इसके ऊपर जब ये ऑपरेटर अप्लाई करते हैं तो वही स्टेट बन जाती है। ओके, सो डज दिस फॉलो? Does it always follow? For example, if you have अगर आपके पास एक ऑपरेटर हो और साइ हो प्लस एक और ऑपरेटर हो साइ हो और ये इस तरह से हो, does it mean that operator A plus B is C?
Only the operator will be here.
All of the operators that we're talking about are here.
Transition operators
It's defined here. Easy equations are defined here.
in physical concept defined here.
I'm not sure what you mean. ये जैसे मैंने कहा ना कि ये कोई ऑपरेटर तो होगा ना जो इस स्टेट को इस स्टेट में कन्वर्ट करेगा, वही है, right? बस I'm not claiming this is Hermitian, unitary, real, blah blah. I'm not claiming anything. It's just an operator. Right? Basically, इसको just a mathematical tool के तौर पे इस्तेमाल कर रहे हैं, यहाँ पे गायब हो जाएगा। हाँ, अगर तो ये true है, this implies this. But does this imply this or not? ये हम पहले भी इसके ऊपर झगड़ा कर चुके हैं काफी, कोर्स के शुरू से लेके अब तक 2-3 दफा झगड़ चुके हैं इसमें। ये imply नहीं करता ये, but this implies this. Why? This does imply this. Because this is true for any incident plane wave phi, and plane waves form a basis. So if this is true for every member of the basis, then this is true in general. Okay? They form a complete set, which means that they form a basis, which means that you can write this. अब अगर आपको याद हो, हमने एक फॉर्म लिखी थी FT. ASA, this was -1/4 pi 2 pi cubed. I believe we were calling this A at that time. 2m over h cut squared ks v psi plus. याद है आपको ये लोग? अगर नहीं तो नोट बस देख ले, पहले अपने आप कन्विंस कर लेंगे कि ठीक है, then we'll proceed. ठीक है? So now I can rewrite this like this: 1/. So let's just call it A again. So this is A. This whole thing is A, and Ks T phi and this, let's choose for phi, let's choose K. So what's this K, right? That's the same K. So an iterative solution for t, if you look up there, just keep on putting back. For t, you will get an iterative solution will be t is equal to v plus v over e minus h naught plus I epsilon v plus v1 over e minus h naught plus I epsilon v1 over e minus h naught. And just keep on going. Right? ठीक है? उस इक्वेशन से and now you can recognize that this is the first order one approximation. This is the second order. This is the third order. And the order means the number of times this V appears in there. ठीक है? यहाँ पे मसला हो रहा है? वहाँ से राइट हैंड साइड पे T है ना? राइट? तो वही उसकी जगह पहले अगर आप ऑर्डर बाय ऑर्डर चल रहे हैं पहले V को 0 कर दें तो T 0 हो जाएगा, वहाँ पे डाल दें V बन गया, फिर V डाल दें वहाँ पर, दोबारा डाल दें उसको, फिर जो बन गया उसको दोबारा डाल दें तो सेकंड टर्म बन जाएगी, फिर इस सब को डाल दें फोर्थ टर्म बन जाएगी, and just keep on going.
फिर इसका प्रयोग नहीं है।
ये तो हम यूज करेंगे ना, अब इसमें ये डालेंगे तो फर्स्ट अब इन दोनों को देखें, अगर मैं सिर्फ यहाँ तक रहूँ, this is just the first order bond approximation. So this will give you the second order bond approximation and third order and so on and so forth. Right? Questions? Questions? Okay, so so I can write f like this, f of ks k. This is n is equal to 1 to infinity f of n ks k, where this n means the term that has n number of v's in it. So, for example, f1 f1 k s k, this would be minus 1 over 4 pi of a, it would just be a, and ks be k, f2 ks k is going to be a, ks be 1 over e minus h naught plus I epsilon v k, and so on and so forth, right? So you can just keep on going to the nth problem. Suppose you want f2, you want to calculate this. So let's write it out. Let's open it up. So this is going to be a. And now how would you do it? So you would have to, let's wait. So ks x, x v x prime 1 over e minus h naught plus I epsilon x double prime v x triple prime k. And then you would have, how many do you have? 4 and then you would have dx, dx prime, dx double prime, dx triple prime. Right? Okay. Okay, let's look it up now. So it will become A. इसको कैसे खोलेंगे? ठीक है. माइनस और ये क्या है? बस it's a localized potential. And what is this? Yes, what is this? Delta function. Why would this be? Yes, it means function. We've already calculated that, and now you can see how easy it is. Once you've calculated the means function, and now you don't have to worry about anything. This, and then v of x double prime, delta of x double prime minus x triple prime. These are all delta cubes, if you want. And then e to the I k x triple prime, and then for these, and then this goes away, and x prime becomes x, and this goes away, and this becomes x double prime. Okay. Where's another v? What happened to another v? Oh, there are two v's. So, and then so there are these two of these left, and you have dx and dx double prime. And so this is a integral e to the minus I ks minus k. Oh no, that's not right. That's not. It's minus ksx e to the I kx double prime and g plus x x double prime v of x double prime d of x d of x. This might be looking slightly confusing, but it's actually very intuitive. Why is it very intuitive? You have a scattering center, right? There is something coming from this direction. So this is k. Right? This is k direction. And you're measuring something here, which is ks. Does it make sense? Right? You don't know what is happening inside. All that you're doing is looking at this region, and you know about this region. You don't know anything about what is happening inside. Right? So the first order Brown approximation says, if you look at it, right, what it says is that you're coming in this direction and you are scattering in this direction, like this. Second order says that it's not necessary that you would just scatter from one point. You could do something like this. Go here, and then go in this direction. So what is this point? This is x. I should have, by the way, if you want, we can just put x prime here, x prime here, x prime here, x prime here. Right? Because primes indicate source. So this is x prime. So you scattered from x prime, and then this term took you from here to here. And then you scattered from x double prime, eventually going in this direction. So what do? You integrate over all possible x's and all possible x primes. And every time this Green's function takes you from one point to another. So this Green's function is something like propagates you inside from this point to that point. And so the third order would be that you would come scattered from 3 points and then go in this direction. Right? So you can just by looking at these diagrams, you can construct these things. उसमें 3 टेलर आएंगे, 2 जी, ये एक जी यहाँ पे आएगा, एक जी यहाँ पे आएगा, ये एक्स प्राइम होगा, ये एक्स डबल प्राइम होगा, ये एक्स ट्रिपल प्राइम होगा. So you are coming in, right? And then you have a g, then you have e to the I k x double prime, then we have a g. Sorry, this is not. You're coming in, then there's you're coming in, then there's a scattering at vx prime, then there's a g that takes you from here to that point, then there's scattering at v double prime, then g takes you from double prime to triple prime, and then there is scattering at v triple prime, and then you're off e to the I kx. And integral over all of ex by v. Exactly. This is something like that. अच्छा लाइट के लिए आप इससे नॉन रिस्ट्रिक्शन नहीं कर सकते. Right? This is basically just a very low energy, not very low energy, but low energy electron scattering. Non-relativistic. And I say non-energy and non-relativistic. Okay? नहीं यहाँ पे सरफेस कोई भी नहीं है. ये आप चाहे तो ये सैंपल सिर्फ एक इलेक्ट्रॉन हो सकता है. एक इलेक्ट्रॉन है और एक इलेक्ट्रॉन आ रहा है, तो लेकिन वो इलेक्ट्रॉन जो है इस पिक्चर में एक जगह से स्कैटर हो सकता है, 2 जगह से हो सकता है, 10 जगह से हो सकता है, 25 जगह से हो सकता है. लेकिन जैसे जैसे आप ऑर्डर बढ़ाते जाएंगे, क्योंकि V बहुत कमजोर है, बहुत वीक है, अगर तो ये स्ट्रॉन्ग है तब तो आप बॉन्ड अप्रोक्सीमेशन यूज ही नहीं कर सकते. देन दिस इज नॉट वैलिड. बट अगर ये बहुत वीक है, जैसे इलेक्ट्रॉन दूर रहेंगे, राइट? सो देन बेसिकली अगर आप एक पॉइंट से कैलकुलेट कर लें, आपको तकरीबन जवाब मिल जाएगा. लेकिन अगर आपको ज़्यादा चाहिए, देन यू गो टू द सेकंड ऑर्डर. अगर आपको मजीद एक्यूरेसी चाहिए, देन यू गो टू द थर्ड ऑर्डर. बट दिस इज गोइंग टू बी सक्सेसिवली स्मॉलर बिकॉज ऑफ दीज बीज दैट आर कमिंग इन. Questions? So, sometimes it is necessary to, especially when you have spherical symmetry, right? So, instead of talking about these things, you want to talk about spherically symmetric states. For example, if you're, and especially if you're interested in the scattering of different L states, right? So what happens? You, instead of the plane waves in the final state, you're interested in the spherical states in the final state, right? But you've already calculated this, and if you knew the transfer function, so let's say that these are the spherical states, then all that you need to do is calculate this, right? So if you know the transfer functions, you can go from one basis to the other basis, right? I'm not going to do this, but if you were to calculate these successive approximations in this basis, this is called the partial wave analysis. And basically what you have to do is calculate these things. You understand what I'm saying? Right? So this is something that I've not been able to do, right? If you guys want, we can either do this or perturbation theory, right? So I decided that we should give at least something on perturbation theory. Okay. So I wasn't sure how much of the perturbation theory people knew, right? And since every time we start poking around something, we sort of feel like we have to do it. So, and since perturbation theory in that sense is very important, so maybe we should do that. And besides, the mathematics involved is slightly more complicated, and you have to be sort of, well, I don't want to say. क्या हुआ? हाँ, exactly. ये वही लेजेंडर और स्पेरिकल और हैंकल जिसमें आप लोग जो है वो आपके हाथ पाँव फूलने लग जाते हैं. So yeah. Yes. Anyhow, Griffiths has a nice sort of nice thing with it. Anyhow, so let's do perturbation here. Any questions by the way? अच्छा, आप मुझे बताएं कि आपको perturbation theory कितनी आती है? क्या करनी आती है? हैं? Griffiths वाली आती है. तो पहले ये बताएं perturbation theory कब यूज करते हैं, होती क्या है?
minor perturbation आती है तो bases होती हैं.
अच्छा, पहली बात ये है कि अगर आपका हैमिल्टोनियन टाइम इंडिपेंडेंट है तो जो एवोल्यूशन ऑफ द स्टेट है वो इस इक्वेशन से कैलकुलेट की जा सकती है, राइट? इफ यू वांट टू मेक इट, ठीक है? ये बात क्लियर है सर? अब कभी कभार ऐसे होता है, most of the time what happens is that this age is very complicated. But sometimes what you can do is that you can write this age as a sum of something that you already know what the solutions are, plus a small thing on top of it, right? For example, this could be the simple harmonic oscillator put in a small electric field. Simple harmonic oscillator might have a charge, or the spring that you're using for the simple harmonic oscillator that has a small defect somewhere in there. So instead of trying to solve the whole Hamiltonian, which might become very difficult, you can guess the eigenstates, the eigenvalues and the eigenstates. You can approximate the eigenvalues and eigenstates if you knew this. And this was small, and you could calculate the matrix elements of this thing in the eigenstates of each one. Right? That's what the thing is. And if you were to do the analysis, right? So there are many assumptions. For example, you say, so if you're doing non-degenerate perturbation theory, right? You would say, which means that this is non-degenerate, right? For example, simple harmonic oscillator in one dimension, this will be non-degenerate. So you would say that the eigenstates of this thing, right? Could be written as psi naught plus psi 1 plus something like this, where this is, if this thing is small, right, then you would have an expansion in orders of something like this, right? And you already have this equation, and you correspondingly also assume that En can be written as E naught plus lambda E1 plus lambda E2, like this. You put these two back in this equation, and then you compare orders, and that gives you approximations, or that gives you sort of approximations for this in this series. So if this is small, then these things are successively smaller. This would be the first order approximation. So you want to estimate this. This is basically this, plus a small chain. That small chain to first order is just this. If you want to further get a better number, you can calculate this, and so on and so forth, right? And E1 is equal to what? So when you do this and compare orders, what does E1 come out to be equal to? And then you can take lambda over
I'm
1.
going to state
Yeah?
the expectation value of the perturbation in unperturbed state.
Right. So this would be psi 0, H1, sorry. Right? Where did lambda go?
So
Let's first order. First order नहीं आना है.
हाँ, अगर आपको लैम्डा चाहिए तो E1 निकाल के आप लैम्डा से मल्टीप्लाई कर सकते हैं, right? Lambda is like a switch where you go from 0 to 1. Okay? So this is the perturbation that you can turn on and off. Okay? And this gives you the full range going from 0 to 1. So this is like a switch that you can, a dial that you can rotate. So if this is not 1, if this is less than 1, then you can just calculate E1 and multiply by lambda. Right? And what is psi 1?
Sir, a combination of the unperturbed bases. Except for the size.
So what should I write?
So your summation,
Summation
coefficient A_n.
A_n. What is A_n?
How we are combining the states and
Combining states.
and eigenbases of H top.
So H1n, psi m, psi n, something like this, over En minus En naught. So naught means, maybe I should put these here.
We already done.
So m not equal to n. Does it sound familiar? Eh? I'm not sure what you're asking. ये एक ही टर्म नहीं है, ये सब है.
अगर हम ऊपर वाले वाले के साथ हैं, ये ऊपर वाली वैल्यू जो आपने निकाली एक पूरा
हाँ पूरा लिस्ट होता है. हाँ. ये तो मैं आपको बता रहा हूँ कि आपने ये 10 दफा किया हुआ है. So ये है. अगर आप चाहते हैं इसको देखना, you can do this. Bilal, is this correct?
No, I can state here.
Oh, I'm sorry. There's something wrong here. is correct. I think this is correct. Why would they? I repeat, right? So ये जो साया 1 है, right? ये मुख्तलिफ जो states हैं, यहाँ पर 1 तो नहीं आएगा, यहाँ पर 1 तो नहीं आएगा। Oh, I see. Like क्या mistake there? Oh, I see. ये mistake है. Copy करो. Side N1, side N1, side N2, right? And so this is side N1. Now this is correct. ठीक है और अब इसको n नहीं कहना चाहिए ये n हो गया ठीक है फाइन दिस इज n ये n है क्या n और ये सम ओवर m है n नॉट और ये भी हो सकता है कि ये उल्टा हो हाँ तो भी उल्टा है ये m है और ये anyhow so if you don't have any questions on how these come about and how you use them right. Then we'll start with the degenerate perturbation theory next time. Okay? And so one lecture on degenerate perturbation theory and one lecture on time-dependent perturbation. Okay? Any question there? If you want to see an example, the example could be if you put the oscillator in a constant field, right? So there's a uniform field E. This carries a charge plus Q, right? And you want to see if there are any changes to the energy and the state. So by the way, you can also write E2, En2. So this is En1, N1, right now. Right? And so you can also calculate this, and this basically comes out to be, and again here we go, psi n naught h1 psi n naught square, right? Divided by E m naught minus E m, something like this. And I'm not sure about the sign there. Is it E m naught minus E m naught or E m naught minus E m naught? I think it's E n minus. And then the sum is the same. So you can try and calculate all of these things for this, right? First you will have to calculate H1. H1 would be so the force is going to be Q E, and the potential is going to be minus Q E X. Right? And so, if you want to calculate, let's say, En1, that is going to be N, let's say, if you want to calculate the first order change to the ground state energy. in which case this is going to be 0 minus q e x 0, and this thing is 0. Why is this thing 0? हाँ, अगर उस तरह देख लें या फिर ये जो है ये गॉसियन है और इवन है ये ऑड है, so that will give you 0. ठीक है, और अगर आपने ये बाकी चीज़ें कैलकुलेट करनी है, then you will have to calculate the rest of the matrix elements. So for example, you will have to calculate 0 x1, so that is going to be equal to 0 a plus a dagger, some constant alpha outside 1, and so this is going to be alpha 0 a 1, which is alpha, and the rest of them are going to be 0. So this is the only thing that will contribute. So psi 0 of 1, this thing is going to be equal to minus q e, and then alpha 1 over h double a. This is basically psi and psi 0, psi 1 not. Okay? And then you can go ahead and calculate. So the first order contribution is 0. That's because but since the first order change to the state is not 0, then this will become not 0. And so if you want to calculate that, I have to leave now. If you want to calculate that, then this would be simply be mod, so 1 psi and 1, this is the only non-zero term, and this is minus q e alpha over h cat omega, and you just put it back in there. So e2, this thing e02 is going to be q squared e squared alpha squared over h cat omega squared. Does that sound right? Yeah, fine. Maybe there is some mistake somewhere. But that's in principle how to do it. So next time we'll start with the degenerate perturbation.